Hello guys, so this is gonna be the first video about chapter 3. I'm gonna be trying to keep this video short. Um, so this is just gonna be about the first section, section 3.1, which covers intrinsic semiconductors. So for this videos, I'm gonna have the key points on the top left part of the screen so that you can easily see what are the main takeaways, what we're being using in other videos, and what's useful for you to know in a quiz or something like that. These videos are created more as a review from chapter 3, so I would definitely recommend you to read the chapter before coming here, or at least read the section before looking into this video. So what I have here is just a part of the periodic table. I took this image from pveducation.org. That's a really good website if you want to learn about photovoltaics or solar cells, but it also has some basic concepts on semiconductors which are the same as what's covered on this chapter. So if you want to learn a little bit more, that's a really good website by, I guess, Christine Honsberg and Stuart Baldwin. They're both from Arizona State University, so if you guys want to go check them out, that's a really cool website. From this periodic table, what's important is the elements that are in blue. Those are more commonly used for creating semiconductors, and I will also include boron here, and I'm going to talk more about that on the next video with doped semiconductors. From this part, what we need to learn is what are single element semiconductors. Those are created from group 4 right here, and it's just basically taking one, as it says, one single element. The one that we use the most is silicon. These elements have 4 valence electrons. I don't know if you remember this concept from your basic chemistry. So you have an atom, and on the outer layer you have, on this case, depending on the group, the number of electrons that are on that outer layer. For silicon, that's 4. So you have 1, 2, 3, 4 electrons. These small dots right here is what's going to represent your electrons. So you have silicon. Silicon has 4 valence electrons and it's from group 4. You can also have compound semiconductors. Those are made from elements from group 3 and 5. You can combine 3 and 5 and get, let's say, gallium arsenide. That's very common. So you have gallium arsenide, and you can also have indium phosphide, I think it's called. So you have indium phosphide, that's another common one. Or you can also combine elements from group 2 right here and group 6, that will be. So an example of that is cadmium telluride. So you have cadmium, sorry about this, is cadmium telluride right there. So these are your 2 types of semiconductors. And on this book, and I think on this chapter, we're gonna just focus on silicon, which is a single element semiconductor. At 0 degrees Kelvin, so this will be at 0 K, your silicon lattice looks something like this. I'm just kind of like zooming in to the basics. Silicon lattice is just like your silicon semiconductor. You have, let's say, this black silicon on the center has its 4 valence electrons, and then it's surrounded by several more silicons. I'm just using different colors here to show what electrons correspond to what element. So you have 4 silicon electrons corresponding to the black one right there, but it's surrounded by 4 blue silicon, and those those silicon atoms share one electron to this. So each one shares one atom to this black silicon, and as you can see right here, they're forming a covalent bond. So when each pair of when you have each pair of share electrons, it forms a covalent bond. So, and this keeps the whole lattice together. At room temperature, however, there is enough thermal energy to break these bonds. So let's change to, I'm gonna raise this, so to room temperature. Let me write, sorry about this, at room temperature, you have enough thermal energy to break these covalent bonds. So by breaking covalent bonds, you are creating, you're freeing electrons and created what's called a hole. So let's take this one for example. It leaves behind a hole and the electron gets free. So this free electron is just moving across the lattice, and this is obviously what creates conductivity. So before getting ahead of myself, I just want to point out holes are the absence of electrons. That's one cool thing, or what good thing to remember. And holes are positively charged. So they have a plus charge. And as you know, electrons have a negative charge. One tricky thing about holes is they're not a physical carrier. They're not a physical thing. They're just the absence of electrons. But they're very useful for us, so we take them as if they were something physical in there. One thing that I have here in my notes is the increase of electron-hole pairs. So this right here, let me get this right here. Oh, I'm sorry, I think I erased that guy. And this right here is an electron-hole pair. So you feed one electron, you have one electron left behind, so that's an electron-hole pair. And obviously the increase of electron-hole pairs results in an increase of conductivity. So the more electron hole pairs you have, the more conductivity you have. So you have more electrons free to move across the lattice, and that creates more conductivity. Another concept that I have is generation. So generation here is what we have right here. So at room temperature, you have enough energy to break the covalent bonds. You create an electron hole pair, and that's called generation. Recombination, however, as you may guess, is the opposite of that concept. So let's say I have this hole right here, a black hole right here. Sorry, just a hole right there. And then there's this electron, this E minus, I'm going to call electrons like that, is free moving across the lattice, and it gets attracted to the hole. So you know the negative charge, positive charge attracts. So this electron is attracted to that hole. It gets here, recombines, and now it's part of that silicon atom. So that is called recombination. What else we have? Intrinsic semiconductor, that's another important concept. That's what the chapter is called. Intrinsic semiconductors are undoped semiconductors, so it's related to undoped. We're gonna learn about what doping means on the next video. But for now, intrinsic semiconductors are undoped, and the electrons hole pairs corresponding to that, so the E hole pairs corresponding to this semiconductor are just created by thermal energy. So a little bit here, created by thermal energy. energy. Then we have another concept called band gap. Band gap is just the minimum energy required to break a covalent bond. So the energy that it took to create this covalent bond right here is called band gap. For no, I don't have the actual numbers. I don't think you need them, just so you know the concept. We have different things right here. I'm going to see here on formulas and constants. Some important things to know is this guy right here, Ni. That is the number of carriers in a unit volume of intrinsic silicon. So this is the number of electrons and holes that you have on intrinsic, or the electron hole pairs that you have on intrinsic silicon. As we learned with room temperature, from each electron that you have, you are leaving behind one hole. So the number, so this Ni is going to be equal to the number of electrons, which is equal to the number of holes. So important things to know, this little n right here is the number of electrons. This P right here is the concentration of holes, which is basically the number of holes that you have. This is found with some constants. You have this V constant that's that depends to the element. You have temperature, so that this V is material dependent. So it depends on the material that you have. That's what I wanted to say. Then you have this E minus the Eg. This is why I mentioned band gap. This is the band gap, which again is the minimum amount of energy required to break a covalent bond. And then you have 2 kT. We know that kT is Boltzmann constant. Let me see if I can write this right. That's Boltzmann. It's a double N constant. And this one is equal to 8.62 times 10 to the minus 5 electron volts per Kelvin. I'm going to talk a little bit about electron volts afterwards, and this T right here is just temperature. And this is how you get the number of carriers that you have in an intrinsic silicon, which is this Ni. So from here I mentioned electron volts. That's just the unit we use to measure band gap. This is equal to 1.6 times 10 to the negative 19 joules. In case you remember joules, it's used to measure energy. And just so that you guys know, if we have, so from this formula on top here, we can play with it a little bit and have the number of holes times the number of electrons equals to this intrinsic concentration square. I like that. I'm going to call it intrinsic carrier concentration. And just so you know, for silicon, this Ni is equal to, sorry for moving this around, 1.5 times 10 to the 10. And the units are centimeters to the negative 3. So this is the number of carriers that you have per centimeter cube. And that's all that I have prepared for this chapter. So important things to know, electrons are here on key points. Electrons are negatively charged, holes are positively charged. We call electrons and holes, we call them carriers. And what's intrinsic silicon? from down here, you know that intrinsic silicon is undoped silicon, and the electron holes created inside of it are just created by thermal energy. So you don't have any outside thing creating this. So we're gonna cover a little bit more of this on the next video of doped silicons, which is chapter 3.2.